All right, I think we're just a couple minutes past 10 o'clock, and we'll go ahead and get started today with our Prognostic Health Management webinar series for the Adaptive Remaining Useful Life Estimator, ARULE. So today's presentation will be done by myself, Wyatt Pena. I'm the VP of Operations, and I'm joined by our Applications Engineer, Arsh Nadkarni. So for today's agenda, we'll start out with a company overview. We'll cover the PHM frameworks and the IEEE 1856-2017 standard, and then do a technology overview and cover some of the development history for ARULE. And then we'll have some time for battery R&D applications, the ARULE GUI operation, embedded applications for ARULE, and then a a set of real-world examples, a summary, and then a Q&A. So here we have a short video introducing our company. So Ridgetop Group, we were founded in the year 2000 and we're headquartered in Tucson, Arizona. Our primary market segments include aerospace, energy, transportation, defense, and industrial IoT applications. And we are a technology leader in the design and development of reliability engineering solutions with a heavy emphasis on condition-based maintenance, prognostic health management, and integrated vehicle health management solutions. We also offer engineering design services and circuitry for harsh environments. And we are also an AS9100D and ISO 9001 certified facility. So today I'll start out by introducing the traditional reliability bathtub curve, where this has been used in reliability engineering textbooks for several decades. So when we look at the failure rate and useful life of electrical systems, mechanical systems, or electromechanical systems, this is a very relevant type of concept to look at how systems and subsystems wear out and degrade, and how the remaining useful life or actual useful life is applicable for a particular time period or duty cycle or application. So the evolution of maintenance practices is something that Ridgetop has been well aware of for over 2 decades. And a lot of the solutions we've developed help our customers transition from reactive maintenance, where an unexpected failure mode happens and causes a disruption, to evolve into modern maintenance practices such as condition-based maintenance, where you have sensor nodes to monitor a given system or asset, and then you can perform maintenance based on physical evidence of degradation based on that data. And over time, condition-based maintenance can be used to develop condition-based maintenance plus or prognostic health management types of solutions, which allow you to transition to more of preventative maintenance or prescriptive maintenance when you can predict when a failure mode is going to occur. So a lot of the hardware, firmware, and software solutions that Ridgetop has developed over the years are really geared at developing these types of solutions. And we have a lot of different technologies for power supply prognostics, battery health modeling and simulation, and as well as industrial IoT solutions for collecting sensor data and fulfilling the IEEE PHM standard and the functional blocks associated with that. So We'll go into that into a little bit more detail on the following slides. A PHM ecosystem is important to understand, and this slide shows how there's 5 key functional blocks in a PHM ecosystem. And it all starts out with the data acquisition and sensing phase for a critical subsystem, which is then used for analysis and prognostics, which helps identify design improvements or maintenance action items, and also determine the health assessment and perform advisory generation or health management actions to perform a certain maintenance activity or automate a maintenance activity or an inspection to repair a given system or line replaceable unit. And over the years, Ridgetop has conceptualized the PHM frameworks in several different manners. And one of our late colleagues, James Hoffmeister, he had came up with this diagram several years ago to really capture, the key elements of a complete PHM system. And that includes things like a sensor framework for your data acquisition, feature vector framework to extract feature data from raw sensor data, and then having a prediction framework to process feature data and then do predictive analytics based on that. And in doing that, there was also a need for performance and validation, which is highlighted on the right, and then the fault management framework, which is synonymous with health management. So this is kind of another way to look at the same diagram from the previous slide, just with a lot more detail and the need for hardware, firmware, and software elements to be integrated into a point solution, and also have that control and data flow framework all working together. And here we have the IEEE 1856-2017 standard and the PHM functional model. So here we can see the 5 core PHM operational processes, which are then distilled into 8 functional blocks. And starting from the bottom and going to the top, we can see where there's the sensing and data acquisition functional blocks, then there's data manipulation, state detection, health assessment, and prognostic assessment. So those 3 comprise the analysis operational process. And then we have advisory generation and health management. Each of these are integral when designing and developing a complete PHM system level solution, as Ridgetop has done for several different applications. And on the standards committee for the IEEE Reliability Society, James Hoffmeister contributed as part of the working group for this particular standard. And now Arsh and I are contributing to some updates that are currently ongoing for the 1856.1 standard that is currently in design and development. So for today's webinar, we're really trying to focus on our adaptive remaining useful life estimation software, which is shown in the top right here for the GUI implementation, or graphical user interface. But if we look underneath the GUI, we can see that this is a 3-stage PHM system architecture, which means ARULE allows us to take condition-based data, which can be arbitrary from different types of systems and data nodes, and then we can extract feature data from that and then do a prognostic assessment to determine the state of health, remaining useful life, and prognostic horizon. So this is a very flexible system architecture that we have implemented into a GUI tool, which is very useful when there is historical data that shows some type of degradation, but it can also be embedded into certain applications or microcontrollers. So we'll be talking a little bit about that today, and the design and development of a Python-based API where we have integrated this solution into other products at Ridgetop. So in summary, ARULE is a prognostic reasoner that allows us to determine the RUL and state of health of critical systems by processing feature data, and it delivers fast and accurate prognostic assessments for the state of health, RUL, and prognostic horizon, which are all key condition indicators for a prognostic application. And some of the key benefits include cost efficiency, improving safety and reliability for the systems where we're monitoring for future data. And then it is very flexible and versatile across multiple different applications and different types of systems. So we've processed failure mode data from electrical systems, mechanical systems, and combinations thereof. So the technology history and development of ARULE took several years, and some of the original R&D was done with research projects through the SBIR program or Small Business Innovation Research Program with NASA and NAVAIR. And with that, we were looking at several different types of failure modes, including certain anomalies for electromechanical actuators, power supplies, as well as batteries and of lithium ion and nickel metal batteries as well. So the technology started out as a prototype that was done in MATLAB, and we evolved into several different implementations from Java to C to Python and even newer programming methods in today. So in today's applications, when we look at the core areas that Ridgetop is focused on, we have a heavy focus on battery health management, which is complementary to the collection of battery health modeling, simulation, and analysis software tools that we utilize and develop in partnership with Idaho National Laboratory. And then we have aviation and aerospace electronics that we monitor for several different failure modes for our customers. And then we also have several industrial IoT applications where we look at doing vibration analysis or time domain analysis on certain gearbox systems or bearings and wheels, such as that in the railroad industry, to determine the state of health and remaining useful life of those key systems and subsystems that we're trying to monitor. So some of the battery R&D applications is something we haven't highlighted in previous webinars for ARULE. So this is something we plan to do today. And here on the right, we can see two different plots for some of the lithium ion testing data that was done with NASA through one of those early stage SBIR contracts. And here we can see there was approximately 475, I believe is the correct number for days, and they set a functional failure threshold at about 32.5% for the rise of internal resistance. And here we can see the fault to failure progression signature or FFP signature of this rise of internal resistance serve as a type of feature data that ARULE can process and determine the remaining useful life. And for each data point that was acquired in this particular set of battery testing activities, we can see there was a new prognostic assessment generated to then predict that future time of failure. And so ARULE again allows us to analyze key health indicators like the rise of internal resistance, capacity fade, power fade, and also changes in ring down frequency, such as those observed in switch mode power supplies. And then we take that feature data and we can transform it into a fault to failure progression or degradation progression signature. And it's also proven across multiple battery chemistries and suitable for other diverse applications, including hybrid vehicles and military equipment. And on this slide, we can see another example where we're looking at the best case, average case, and worst case capacity loss that is simulated from one of our battery health modeling and simulation tools called CellSage. And we can define a functional failure threshold at approximately 20% of a nominal capacity loss. And here we can see, based on processing that data with the modern ARULE GUI, we can get a very clear progression, linear progression for the state of health plot, which is shown in the lower left plot of the image for ARULE. So very, very useful in terms of normalizing the feature data that is serving as the input and then doing Kalman-like filtering or extended Kalman-like filtering to do that future prediction for state of health and remaining useful life. It's also important to note that ARULE can be designed or implemented to account for several nodes and not just a battery management system or for a particular battery pack, but for any given system that you're trying to monitor. So it is all defined based on your system definition list and then your node definition list. So you could have several system definitions all pointing and linked to several different node definitions and process this data very, very efficiently and quickly. So now I'll turn it over to our applications engineer, Arsh Nadkarni.
Thank you, Wyatt. Uh, Hello everyone. So let's go ahead and talk about the ARULE GUI operation. Before we kind of look at the GUI, it is important to understand the definition files that are used for this program and a very specific file structure that it has. Next. So ARULE basically works with two types of editable files that we call definition files. There's system definition file and node definition file. So the system definition file basically defines the number of sensor nodes that you're trying to monitor in the system, and the node definition file defines the name of the file that contains the input data from those nodes you're trying to monitor. The node definition also defines your prognostic parameters and values, anything you see in that input data that you want to feed into ARULE. And then also directory paths for output file, log file, and system files. And another feature we call the support checkpoint restart, which I'll talk about later. So definition file, input data files, output data files, and the CPT files are kept in a very specific data structure that is shown down here. So you have your main ARULE directory, and under that you have two other directories, the definition subdirectory and the data subdirectory. Next. So a system definition file, again, it defines the nodes of a system. And inside ARULE, we currently support about 25 system nodes, and we could increase or decrease that upon an application basis. Next. Node definition files, again, they define values for all keywords in node definitions, and you only need to specify those keywords specific to your case or whatever project you're working with. There are two types of keywords and values, data dependent and file dependent. They're shown in these tables here. So file dependent keywords are basically your input output file and the type, and your data dependent keywords and values, they mostly come from your input data and the project you're working with. Next. So shown here is what the ARULE GUI looks like. The top half is your data input half, basically, where you define your node and system and node definition files, and then run ARULE. And the bottom half is your data output half, where you can visualize outputs for multiple ARULE runs. So to the top left here, that's where you start. You start by setting up a system definition. Inside that system definition, shown here, marked as 2, you can set up your node definitions. And following that, you move to the right. You verify if your in whatever inputs you gave it are correct, and you can also preview the input feature data that you give it. And once you find that everything is right, you can go to the right and run ARULE. So you can either run ARULE for all input data points that you provided, or we also have another mode called the support checkpoint restart, where you can run a specific number of data points that you can define, shown here by the run radio button and the text box. So let's say I give it 50, it would only process 50 data points at a time, and you'd have to keep running it multiple times until it converges to a good output. Finally, once you have your ARU runs, you can visualize them down in this bottom half, where you can see your input feature data again, all the transforms that ARU has done, and finally your state of health, remaining useful life, and prognostic horizon down here. Next. Now let's go ahead and look at ARU as an embedded application. Next. So before we look at how ARU was embedded into other applications, let's go ahead and look at the command line interface for ARU. So that's something we call UD-ARU or user-defined ARU. So UD-ARU is an executable program that uses ARU 2.0, and the diagram for that is shown here on the right. So UD-ARU can be either run on a Linux or a Windows machine as an executable file using any sort of command line interface, terminal, Windows PowerShell. Uh, and UD-ARU basically accepts 5 input arguments, which are your SDEF file name, the ability to log, your support checkpoint and restart operation, your build new CPT files, and the main ARU directory that we talked about earlier. So shown below here is how you call UD-ARU on in a command line interface. You can basically pass the above 5 input arguments. And then this is also an example down here that shows how UD-ARU is called in a Windows CLI. So you give a UD-ARU.exe demo2101 and then that final ARU path. So here the SDEF file being used is demo2. We have enable logging, and then there is no CPT mode used. It's just gonna process all data points. It will build new checkpoint files as well. And then lastly, that's the final, the main ARU directory again. Next. So we took UD-ARU and then we ran it in Python. So that's our ARU API that we call ARU for Python. We use the subprocess library within Python, and so you can import it. You can give it the same 5 input arguments like before, and then you can call it within a subprocess.run command line. Next. So ARU for Python is available on GitHub. You can go in there, clone it to your local machine, get started on it that way. Shown to the right here is a flowchart of how ARU for Python is organized. So as you can see, the very first folder is your main ARU folder, followed by the demos folder, which houses the scripts to run ARULE scenarios in Python and a few examples, a couple other files down below that for licensing, and then you also have the output plots directory where all your ARULE output plots are stored, and then a couple other utilities to do stuff within the ARULE API, and then finally your ARULE UD ARULE executable. As far as dependencies go, we use all open source libraries, so NumPy, Matplotlib, Pandas, and then term color. These are widely available. And then we also use the Microsoft Visual C++ redistributable. Next. So shown here is what those Python scripts look like for making a ARULE run. So basically, to the top here, we have this pre-packaged variable. If so, if your node definition and system definition files were taken from the GUI version of the ARU, you would specify that as true. And if you're creating using this API, you would specify that as false. A bunch of other things here like your sdef name and the ndef names within that sdef. And finally down here you can call the input parameters that you give it, similar to the GUI, but in Python you have to put all of them in parentheses to sort of create an array. Next. Shown here is the later part of that script, where you can again give it those 5 input arguments and then run. And then there's also this argument called show, where if the user desires to see what the output plots look like as the program is running, then if you declare that as true, you can see those plots that are shown below as the program's running, and then false would just not show them, and you would have them in your output folder for this. Next. So again, very simple to run these Python files. You just go to you set up all the input parameters, your ndef, sdef, and then just go to a terminal and then say Python, whatever file you want to run, and it will do the job altogether. Next. So in the output folder, once the program's done running, you can see output file with your time array, your RUL, pH, SOH, and a bunch of other key prognostic estimates. Next. And finally, the plot. This is the same plot as before, but if the user desires, he can set that the argument and see this while the program's running, or it's saved to the ARU for Python plots folder as a PNG file by default. Next. Now let's go ahead and talk about how we embedded ARU into our Sentinel Motion View software application for the Sentinel Motion product line. So basically, Ridgetop designs IoT sensors which are tailored for harsh environments. We call these RotoSense, and they're able to detect acceleration, temperature, gyroscope, and GPS data. So basically, we have 3-axis accelerometers with a plus minus 200 G range in there, and these can be tailored on an application basis for capturing acceleration and vibrations in different kinds of orientations and applications. Um, Data from these sensors is streamed down to a data management hub called the Sentinel Gateway through a Wi-Fi network. Um, and on this Sentinel Gateway, one can perform edge analytics and customize software capabilities through the single board computer that's present in there. The gateway also allows various connectivity options like Ethernet, cellular, and Wi-Fi. It has a smart router functionality, network drive, and a 1 TB solid state drive, along with a dead reckoning GPS receiver. So once all the data comes into the gateway, one can further send it down to our Sentinel Motion View software, um, where the user can see and analyze this data. One can also control the gateway as well as the sensor from the Sentinel Motion View software. And now within that, we have ARULE embedded. So UD ARULE, the CLI version we talked about earlier, is embedded in there now, and it is we kind of tailored it into a specialized predictive analytics toolbox that was designed to address the early detection of mechanical failures within complex systems, specifically for railroads, aerospace, and other industrial applications. It fully complies with 1856-2017 that White talked about earlier, and has a intuitive web graphical user interface, so that one can upload sensor condition-based data and monitor the health of a target system or a subsystem. Next. So shown here is what ARULE looks like in the Sentinel Motion View software application. One can manage system configurations, so the SDEF and NDEFs, preview the inputs, and then run and track the ARU runs. It also gives you the ability to play around with these output plots, and then there are a couple other features within Sentinel Motion View for advisory generation and health management that you can connect ARU to. So once you have these RUL, pH, and SOH estimates for different data collects, based on that, you can make decisions and generate alerts. Next. This is another application of embedded ARU. The Ridgetop has another product line called Sentinel Power View, which has to deal with degradation power supply system. So the objective is to introduce power supply degradation by decreasing the power supply capacitance with the PCDD, which is the programmable capacitance degradation device, also designed in-house, and observe the performance with the Smart Probe 4000, which is again another sensor uh, to monitor capacitance in power supply systems. Embedded ARU, same again, we use the UD ARU version that outputs the state of health, RUL, and pH estimates for that power supply system. And then that's shown below here in this picture. Next. This is a video of the whole process happening. It usually takes about 7 minutes for the power supply to degrade to 0%. So that's this process where you can see SOH falling to zero in about 7 minutes or so, and corresponding to that, your ring down frequency in the topmost plot is changing as well. Next. Now we'll move on to some real world examples and see where ARULE was used for different applications. Next. First one is our very own XFD4 example that comes with the ARULE GUI. So this example focuses on the ripple voltage type of feature data in power supply systems. Two distinct form of characteristic signatures arise when filtering capacitance is reduced. When the output filter of the supply is a full pi circuit, or when the output filter of the supply is a half pi circuit. Uh, Corresponding to that, step appearances occur because the filtering capacitance was reduced electronically by disconnecting parallel connected capacitors one at a time. So this is actually a manual fault injection technique. And because of that, you see these step-like appearances here in your input data shown to the left below. So in this particular example, we defined one SDEF, namely XFD4, that comprises of one NDEF called XFD-BPS03. And once the whole scenario was run through ARULE, you can see to the bottom right here, you get beautiful RUL and pH plots that indeed show the power supply system uh, failing in about 21 minutes down here. And then corresponding to that, you also have a um, very stable SOH plot that also falls to zero in about 21 minutes. Next. Another application you would see is for spacecraft reaction wheel faults. So this is for simulated data for a 5 and 20% nominal static friction fault for reaction wheels for spacecraft in low Earth orbit. Here, two scenarios are baseline. One time fault, that's when only one fault occurs during the whole duration on one reaction wheel, and then multiple faults where there's multiple faults during the whole duration of the spacecraft on one reaction wheel. Shown down here to the left is the input feature data that was given into ARULE. So basically, whatever raw data was observed, we took a rolling root mean square feature for both cases. Um, and we kind of chunked that raw data with a time window of 10 minutes. So your feature data, as you can see, shown to the bottom right here. Next. And then the RRMS feature data for both cases were fed as inputs, node inputs to ARULE. These are the input parameters we gave it. And so by these plots down here, it is clearly evident that the reaction wheel undergoes complete failure in about 9.8 minutes for the one-time fault scenario and 42.78 minutes for the repeated fault scenario. Um, since the time it starts its mission. Um, and then these were found to be two possible failure modes for this given application. Next, the next application is Ridgetop's in-house testbed. So the experimental setup shown here is a single stage spur gear arrangement, which is ideal for conducting experiments that require various load speed conditions. So we basically mounted two accelerometers, 80XL 325 EBs on the shaft and the bearing, and they were interfaced to the rotosense sensors to proceed with the data acquisition. So here we had two scenarios. The first phase was baseline testing, where we operated the system under both nominal, healthy, and degraded conditions. And then the second phase was your fault to failure progression testing, which was a highly accelerated life test to operate the system until it reaches a state of failure by actually notching faults on in the gear teeth. Shown down here is the test plan for the same. Next. So once we got the raw data for both cases, the shaft and the bearing mounted accelerometer, 12 time domain features were extracted from that using a custom Python pipeline. So basically, we used a single data collection interval, extracted features for that, and then concatenated those features for a temporal observation. Um, and then shown down here is that concatenated feature data. We chose a peak and clearance factor for the shaft and standard deviation peak and peak to peak for the bearing, as they showed good fault to failure progressions. Next. Um, Shown here on top is a chronological visual of the gear teeth. So as you can see toward the on the left here, they're very sharp, but over time, they got completely grinded down. And the interesting fact about this experiment is the gears grinded themselves to failure without any human notching on them. So all this happened automatically, and we were able to observe this failure mode. Um, in the ARULE output plots, you see these distinct table-like features at, at at some points. That's a result of stopping and starting the system multiple times um, to adjust the gears to be in the right orientation. And then the system experienced physical failure around the 16th hour, precisely 15.75 hours. Uh, and it was found that the bearing mounted accelerometer exhibited a faster detection capability compared to the shaft mounted accelerometer. And this was again another possible failure mode for the test bed. Next. Looking at those applications, um, some suggested markets or sectors for ARU would be in the rail or transportation sector, where you're trying to detect wheel and bearing defects and monitor the condition of track to reduce derailments. Likewise, in aerospace and the aviation sector, harsh environments, you want solutions up to 100G, and also in energy and the industry sectors. Next. So in summary, we talked a little bit about the company and technology background overall. Ridgetop is a leader in PHM with a history of innovation and reliability engineering, and ARULE is a robust predictive analytics tool developed with contributions from NASA and the Joint Strike Fighter program, and it aims at providing accurate SOH, RUL, and pH estimates. ARULE also is a powerful predictive analytics tool that can take any kind of arbitrary condition-based data from sensors, and it is available as a standalone software package or as an embedded solution. We also looked at a step-by-step demonstration of the ARULE GUI that detail how users can manage the definition files, input parameters, run ARULE, and then visualize these prognostic estimates for different types of scenarios and condition-based data. That ARULE is very robust in the sense that you can integrate it into any application, as we saw shown in the Sentinel Motion View and Sentinel Power View platforms. And it has a strong role in monitoring and predicting failures in industrial IoT and aerospace systems. It supports predictive maintenance by analyzing feature data and fault to failure progression signatures to forecast failures and schedule interventions from the maintenance team. We also looked at real world examples, including the use of ARULE to predict failures in spacecraft reaction wheels, power supply systems, and then the in-house testbed experiment that described how ARULE accurately predicted the healthy to fail progression of the gears. And these three real world examples validate ARULE's reliability in these kind of scenarios in today's market. Next.
Excellent. Thank you, Arsh. That was a really good presentation on ARULE and the embedded application. So I think now we have some time for some questions, and we'd also like to, you know, dedicate this webinar and this slide deck to the body of work that was done by James Hoffmeister, or Hoffy. He was an excellent engineer, mentor, and leader here at Ridgetop Group, and his contributions will guide us for many, many years.
I have a question.
Yes, go ahead.
What are the future development plans for ARULE, and if there are any new features or updates in the pipeline?
Yeah, that's a great question. So ARULE has been developed over the last 15 years or so for different applications, and the core development is done for packaging it as a predictive analytics tool for a standalone application, and then it has the API architecture to be embedded into other applications. So future development and activities that we collaborate with our customers around is really the deployment of ARULE in their given systems or their PHM predictive analytics platforms. Yep.
Yeah,
Next question.
Yeah, I have a question. I was wondering, how does ARULE account for different environmental conditions or usage patterns in its predictions?
Yeah, that's a great question. So ARULE is actually agnostic to the type of feature data it processes. So different environmental conditions or stress factors that are observed for a particular data node, it can be handled with the feature data extraction process or through the noise reduction techniques that are employed inside of the ARULE predictive kernel. So even noisy data can be accounted for, but typically, whenever you're developing feature data for a prognostic application, there are data smoothing techniques that can be applied beforehand, so that way you can get the most accurate and meaningful estimates from your prognostic reasoner.
Yeah, thank you.
All right. Are there any other questions from anybody? Okay, so I think I do have a couple questions here that we typically get from many of our customers whenever they first start utilizing the tool. So they typically want to know what is the primary difference between the GUI version and the embedded version of AROL. And in the GUI, we know that there's a 25 node limit to process for each system definition file. And in the embedded version, we can actually extend or customize that for any given number of nodes. As we know, many complex systems have several different types of data nodes and therefore feature data extraction results that need to be processed. And we also offer a whole suite of reliability engineering tools and services for conducting things like a failure modes and effects analysis, FMEA or FMICA, and we can provide those insights and reports for customers and their given systems. So what we typically let our customers know is the hard part about prognostics isn't necessarily processing feature data to determine the SOH and RUL. The typical hard part of developing a PHM solution is really understanding the failure modes and the data processing requirements and the sampling rates and mounting locations of a particular application. So with that, we have over 2 decades of experience in investigating these types of failure modes across government, industrial, and commercial applications. And then we also get a question around the software licensing option. So the software is available through annual and term-being licensing agreements. And then another question that we typically get is a list of publications, and we'd be happy to share that as there are several from the many different projects and contracts we've worked on over the years. All right. Well, I would like to thank everybody for their time, and thank you again, Arsh, for providing a very detailed overview on ARULE. And we look forward to any questions that may come in through email or through our website. So, yeah, if interested, we're always happy to collaborate, whether it be with academia or industry or government. Feel free to reach out, and we'll be glad to get in touch. So, thank you, everybody, for your time, and hope you have a great day.
Thank you.